Hi, my name's Simon. I've been putting together a sequence of videos to show you how I constructed this animation of a scroll expander in the Netbeans and Java environment. Just to show you what this actually does, this demonstrates the internals of a scroll expander and how two intermeshed scrolls or spirals act together, orbiting around one another to trap pockets of gas which then expand and generate power. There's the orbit that the dynamic scroll moves around. To do this, you need to be able to handle time slices, to be able to work out what position the scroll moves to, the dynamic scroll, and where the gas pockets are at each time step. So handling time is the first important issue to get to understand. The second issues are all about how to have smooth graphics. What you tend to find is if you update, particularly if you update very rapidly on the screen, you tend to get flashing and poor quality animation. So I've addressed both of these in a total of 4 videos. This is number 2. The first video, let me just stop that one, we looked at the time issues and created a very simple stopwatch. And there's stopwatch running in 1/100ths of seconds. I can stop it, I can restart it, stop it, reset it, and get rid of it. In this second in the sequence, I'm going to talk about the animation, about how we actually get smooth graphical objects on the screen. Very briefly, the environment being used is Java version 8 from Oracle, which is a free download at the moment, but soon won't be, I believe, and Netbeans IDE 8.2. You only need the Java SE version of that. Okay, let's get rid of those off the screen. Let's get rid of myself off the screen as well. Then we'll start looking at this application. Exit that. I'm going to start a new application and show you how you put graphics onto the screen. And then we'll go into a program already written to show you how that then develops into animation. So, a new project, Java application. Let's use the next name that comes up, so we're already looking at this quickly. As in previous examples, we get a very simple Java program here which talks to the command line. So the first thing we need to do actually is to get rid of that. Find the right place here. Here we go. So Java application 16. So I create a new JFrame form. So this is give it a name. Animation demo. Whoops, didn't like that. I've got space in it. Finish that. And as in the last time, that was a rather unusual step here, but we have to kill off the original, because this Java frame here has its own source code, has its own main, so entry point in here is main, and we can't have 2 mains in the package. So first thing we do, before we move any further, is delete the original, safely delete it. It's gone. So we're now just left with this one frame. There's the design. At the moment, just a simple JFrame. There's the source code. Some extra code's been generated, and this will uses the main then to invoke the graphical user interface. Then control will take over from the button presses. Go back to design. As in the last application, we're going to add a button to exit. I'm going to be a bit lazy here and not bother renaming these buttons. But I will put obviously the correct name on it, which is exit. And the second button here, I'm going to lay down, which will display, will draw. I'll show you how it's going to draw in a moment. Make this a little bit neater. And I need a place to draw. I'm going to put a panel, J panel. There it is. And the J panel, so we have here J panel 1, which is the instance of the graphical object JPanel. So this allows us to draw on the screen, what we'll do when we code this. Okay, so let's first do double click on the buttons. First exit, very simple, we just say system.exit, put the return code 0 in it, that's that dealt with. Okay, and then we go to draw. Before we do, actually, I'll just give that a border. There we go. Let's give it an etched border so we can see which bit we're actually drawing in. Double click on draw. So this is the handler for click on the button draw. And this is where we're going to get hold of that panel and start drawing on it. So the first thing we need to do is create a graphical construct which will allow us to draw on there. So we use graphics 2D, two-dimensional. I'm just going to use G as the construct, which is a graphics 2D version of the JPanel 1, and we want to get its graphics. A, B, C, D, E, F, G, great. Get. Trying to go too fast here. Graphics. Okay. So what this is saying, we've looked at one of the attributes of JPanel 1, which is a method that gets hold of its graphics. So we're connecting that to this construct G. At the moment, we haven't found the right library, so we need to either try and fix import. That's happened, that's worked, that's good. So there it is, it's added in AWT graphics 2D. So that's the library that it's found to resolve that one. So we now have this construct G allows us to put things on JPanel 1. So what I'm going to first do is draw an oval on here. So I use G dot, these are all things I can do now with the graphics. I'm going to draw an oval. There we are, draw oval, and it's looking for an X and a Y starting point and a width and a height. And I'll come back to how that works in a moment. Let's put the oval on first. I'm going to put that at 175, that's 175 along, 50 down, I'm going to make it 50 wide, oops, 50 wide and 50 high. Okay, so we actually have something that should now work. Let's go into that. It's the first time we've operated it, if you remember this from the last video, because we had two mains, it's asking me which main should I run, and we're going to run this one. There's the actual application now. We can exit and we can draw. So we click on that to draw. It draws a circle. So it's drawn this circle 175 in to this corner and 50 down, and then 50 wide and 50 high. So it's an oval, but because it's 50 wide and 50 high, it's a circle. Now, before we go into any more detail, it's worth just having a quick look at the coordinate system, just to be clear how that works. So relative to either the screen or a panel in this case, the coordinate system has 0, 0 at the top left-hand corner. X increases going right and Y increases going down. So that might be a bit of a leap for some people. You get used to the idea of graphs that start from the bottom left-hand corner, so Y increases going up. So if as I produced an oval a moment ago, let's look at that. If I want an oval, I have to define effectively its surrounding frame. You don't see that, of course, but that's the point that I'm defining where it's drawn. Not the center, it's the corner of its frame. And then the width and height determine the shape of the oval. And if it's the same, obviously it's a circle. Likewise for a rectangle, x1, y1 is the top left-hand corner of that rectangle. Then it's got a width and a height. So these are the actual calls we used. So just to be complete there, if you want to draw a circle at point x3, y3, that's the center point, with a radius r, then in order to do that, you need to find that top point of the frame first, which is x3 minus r, y3 minus r. So both go backwards. And then it's got to be a width and a height rather than its radius, so it's got to be 2 times the radius and 2 times the radius to be then it's a circle. So that's how that's the coordinate system we're working to. Okay, let's go back to the application. So we've drawn an oval, the position we want. The next thing I'd like to do is draw a triangle, which this is going to be a very simple line drawing of a girl with a red dress, and the red dress will be a triangle. So the triangle, I want to start from the bottom of the circle, which is a head, we need to create this triangle. We don't have a draw triangle. So what we're going to have to do is create a polygon, a set of coordinates, which the application can draw from coordinate to coordinate. It's going to be a very simple example. For the scroll, we have more than 700 points in each scroll that defines their shape. To do that, I'm going to create a two-dimensional integer array. You'll see why in a moment. Called points, and that's a new int 2. Whoops, sorry, wrong brackets. 2, and let's call it 30. So we can have up to 30 points in this if we wished. We're only going to use 4 actually. The reason I made this two-dimensional, and the first dimension is only 2, is that anything that's referenced 0 in the first dimension will be an x, and anything that's referenced 1 will be y. Just a very efficient way. We could do this as 2 one-dimensional arrays of x points and y points. Just think it's a more elegant construct. Rather than draw all these in, because they're going to take a while, to speed things along, here's one I made earlier. And I'll explain what these are. So this is the construct of the x and y points for a triangle. We know that the circle was drawn at 175 and 50. That was the framework for the circle. That was the top left-hand corner. So its centre is 175 plus half of 50. That being the radius is 25, which is 200. There are 200. Let's just separate those out as the first point. And we started the top left-hand corner of the frame round the circle at 50, and it had a height of 50. So we come down 100. So that is the point, at the lowest point on the circle. And that's where we want 0.0 of our polygon to be. So the x is at 200 and the y, reference 1, is at 100. The second point I create, we want to move downwards and to the right. So I go from 200 to 250 to move right. I'm going from 100 to 200 to move down. The third point, so we're moving on the hem of the dress, if you like, at the bottom. We're moving left to 150, so we're moving 100 points to the left, and we're staying at the same y height. Then the final point is the same as the first point. You have to close the polygon up. So we're drawing a triangle. We've now constructed this, so now we can draw it. Draw polygon. There it is. And we're going to draw with x and y points and a number of points. So we're going to draw it as points. This is where the value of how we define it will come out. Points 0. Oops, got the right bracket type. Again. And points 1. So this is a rather handy construct. What it says is if you just define the first dimension of your two-dimensional array, then effectively this is defining a one-dimensional array starting from that 0 point. So it gives you all the x points, likewise all the y points. The two will correspond to each other, of course. And we're saying do that for 4 occurrences. 1, 2, 3, 4. So that should draw the line. And let's see that now. Sorry, left that one running. We'll take that one off. And draw it, and there's the triangle. So that starts from the lowest point there, goes across. Let's just see if we can see the two things together. Hang on, put that down there. So we come across and to 250 and down to 200, then back to 150, 200 here, and then back to the starting point. So we've created the address for Annie. We can fill that if we wish. So just to show, we're going to have to draw lines. Let's change colour as well. That's a new command. So set, and there's colour. And in fact, it's automatically found red for me, which is handy because that's the colour I wanted. These are standard colour codes. You can construct your own colours, if you like, from the RGB, red, green, blue values between 0 and 255, and also the transparency. So I'm going to fill a polygon. So it's exactly the same as that. Let's just copy that. In fact, there, I'll save a bit of time. Copy, paste. There we go. So, and then I'm going to put an outline around it still in black. So I'm just going to say g dot set color, and I'm going to make the color now black. So it's a predefined black color. Okay, so let's see how that's now looking. Draw it. Red dress, outlined, a bit faint, but outlined in black. Great. Okay, I now want to add arms, legs, eyes, nose and mouth. So I'm going to copy in a fair few bits and then explain what I'm doing. So that's all the parts we've already done. So I'm going to first, let's bring in an arm. Bring it all in and then explain how it works. Okay. So save a lot of typing time. This, of course, you can download from the website, so don't worry about trying to get all this. You can download the whole thing in all its different formats. So this is where we got to. We put the outline in black around the dress. We now want to draw the her right hand arm. So that's going to the left on our screen. So I draw a line again from that neck point, if you like, 200, 100, and I've gone down to 150, so I've gone back 50 points in the x direction, and I've gone down by increasing y to 130. So 150, 130 is my elbow. Then from the elbow, I've gone 150, 130 there. I've gone further over to 110, so I've gone another 40 across to the left, and I've come up from 130 to 110. So I've decreased the amount of y, so I come up 20. That now defines the arm, the two parts, the upper arm, lower arm, on the left on our screen, which is her right hand. This is where some maths becomes quite handy, and I'll dive out of it a minute and explain this in more detail. We're using Pythagoras. This would probably make some people feel quite sweaty remembering old maths exams, but there's a few bits of simple maths we need to do this type of animation. So what I'm trying to do here is work out how long that line of this lower arm is, because I'm going to reuse that when I draw the left-hand arm, but at a different angle, but to be the same length. So let me just dive out of here for a moment to explain some basic trigonometry, because it's really important. You can look at this at your leisure. This is downloadable from the website. If you have a right-angled triangle, so that means it's 90 degrees in this corner, there is a relationship between the sides. So the X direction and the Y direction, which in trigonometry terms would be called the adjacent and the opposite, if you're looking from that angle. If you square those and add them together, you get the square of the hypotenuse, the sloped part. So you can also, it's probably bringing back memories to people right now, giving you anxiety attacks. You can work out that h is the square root of x squared plus y squared. You can also, of course, go backwards from that if you know that. If that's a radius, for example, that you know, which could be the length of the arm, you can say that the x direction given a y is the hypotenuse squared minus the y squared, and the opposite way around, the y from the x. So it takes a few minutes to remember how these work, but they are well worth remembering because they allow you to work in this 2D space and make things look right. So in most basic terms, if you've got the length of any two sides of a right-angled triangle, which is always right-angled effectively because you're in an XY space, and you can calculate the third part of it. The other one which you can use is sine, cos, and possibly tan. So the sine of an angle theta here is the opposite y over the hypotenuse h. The cosine of angle theta is the adjacent x over the hypotenuse h. So if you know those, and you can look up cosines, sines, etc. from their angles, you can then work out, again, you can say that if you know the hypotenuse, which could be a radius, a length of an arm, a clock hand, as you'll see in a later video, then you can work out its y position from the angle it's at, which might be given by ticks in a clock, for example, as the hypotenuse, the length of it, times the sine of its angle. Likewise, the x is the hypotenuse times the cosine of the angle. Okay, you can also use inverses of sines, coses, etc. To get the angle for known lengths. That's less likely to be required. So the importance of that is, this is a statement really, is that we're always specifying on-screen points by x, y coordinates. It's a grid system. We're filling in little lights, the pixels in the x, y coordinates. So for if we want the length h to remain the same for given coordinates at one end and either given or x or y length, we can then calculate the corresponding y or x from these formulae. So this will allow you to keep things looking right on screen. It means you've got to do these calculations as you go along. That's the only bit of the maths lesson here. It's not as bad as it sounds. So here I introduce this bit of maths. I'm going to say I want I've drawn the right hand arm. I want to find the length of that lower arm, which runs from 150, 130 xy to 110, 110 xy. So I've used here the length squared, so that's power 2, and the y length squared, added those together and taken the square root of the sum. That gives me the length, the hypotenuse from what we just looked at. And again, we've introduced this before, we use maths round before we turn it into an int. Obviously, pixels can only be 1, 2, 3. They can only be integer. The calculation here is giving us a precise measurement. It might be 52.89. If we just did the int of that, we'd get 52. If we do the rounding of that, then we get 53, which is closer and more correct. So now I draw the left-hand arm. We'll put all this on screen in a moment. I draw the exact mirror image of the upper arm. So I've gone from here, from 200 100, same thing, from the neck point. Instead of going 150, going 50 back, I've gone 50 forward to 250. And the y is exactly the same, so it should be totally symmetrical, the upper arm. I then used the calculated lower arm length for, again, starting from the same elbow point, 250, 130. I've said that I'm going to fix here the X point to be at 270. Therefore, I need to work out what height, what Y value I need to get the same arm length as I had before. So this is using that mathematics. Okay, I'm just going to take that out for a minute because we're not going to look at that yet. I'm going to give it some very simple legs here. Each leg is a leg with no knee in it, goes down and then has a foot. So that's from the bottom of the dress to the ankle, and then that's from the ankle to the toes, and then there's two of them obviously. And I'm going to give it some eyes. I've set those to be blue, and I've set those just as very small ovals, which are going to be 10 wide and 6 high. I've given her a nose, which is a simple set of lines drawn in black. And then finally, and rather difficult, I find, is the draw arc to give her lips, so coloured red. The way that the arc works is quite complicated in my view. Again, you have a frame which starts from the top left. Here I've used 190 and 83 as the starting point. It has a width, which is 20 in this case, and a height, which is 10. Then these make difficult. You need to play around with them. These are the angles at which you set off from the top left-hand corner in that framework to the top right-hand corner in this case. So these are the angles made with the, I think, the horizontal. You need to play around with these to get them right. It's not that easy to follow. So let's have a look at what that now does. Hopefully everything's there that we need. Draw, and there we go. So we've now got rather evil looking eyes, nose, the mouth, that's the arc. We've got the head that we drew initially. There's the arm going to the elbow. That's her right arm and lower arm that we drew. First, we worked out the length of this lower arm, so that we first drew the upper arm to be symmetrical. We then fixed a Y value. Looks like she's broken her arm here. But then we used the mathematics to make sure that that lower arm there is the same length as that arm there. And we put some simple legs on. So we've introduced the mathematics. We've drawn a very simple line drawing. What we see is that the rather evil-looking eyes are because we've got we've only got pixels which can either be blue or not blue. Likewise black, likewise red, etc. So as soon as we try to draw at any sort of angle, we get this aliasing taking place. This is where it's saying, well, I really want to be at position whatever it is, 25.8, but I can't be. I can only be 25 or 26. So you get these lines, these jumps, these aliases. So the next thing I want to do is try and smooth those out. And there's a very simple construct to do that, which I'm going to just copy in so I don't get it wrong. I'll copy in another part as well. Explain what happens there. So what I'm now adding are a couple of things that will make this look a lot better, I hope. Insert. Come back to stroke in a moment. First thing I want to put in here is something called, again, construct G. We're going to set the render hint. So that's the rendering hint we're using is a key for anti-aliasing. And we're going to set that to anti-aliasing on. So this is really where you want half a pixel, for example, 56.2 or whatever it is, or 56.5. You can't get half a pixel. So what it does, it draws in beside your line if you want a black line, for example, it draws in a grey, depending on how much of the pixel you really wanted. It makes everything look much smoother. So turning this on will improve the look tremendously. At the same time, before we go any further, we need to to fix the import for that. And it's saying rendering hints is the one we're after. Okay. And at the same time, it also created this one called basic stroke. Strokes, which I've added here, are where we want to change the thickness of the pen which has been used. So at the moment, we've drawn 1 pixel thick with no aliasing, no anti-aliasing on. So we get these rather sticky pictures. By creating here, we've gone to a 2 pixel wide pen for a lot of the drawing. There we are. Set stroke, stroke 2, which I define as being 2 pixels wide up here. And down here, there we go again. I just took it out before. I've set to 3 pixels for the legs to make them seem a bit more sturdy. So if we now go and look at the image, we should have something that looks a bit more acceptable. There we go. The eyes have become much more like ovals. Seems a lot happier. We've turned we've made the arms thicker, the outline thicker, the legs even thicker still. And there's still a dash of aliasing going on, but nothing like what it was before. It's a much, much smoother picture. Okay, so we've definitely worked out how to improve the looks of the line drawing. Okay, the next thing I want to do is to actually start moving this around. Now, rather than trying to do this one step at a time on the screen here, I'm going to go to the existing package I've written. This is the one you can download, because otherwise it would take a long time to do. So let me show you what's actually on this package first. So we've drawn the simple Annie. We did that earlier on. We can clear that. We can draw it smoothed. I can draw her with sturdy legs, so thicker lines to look better. So that's where we'd got to on our own version. Because we've now calculated the length of that arm, what I can do is move that arm around. So here, this slider, I'll explain how that works in a second, allows me to fix an angle to the horizontal, and I can then move it round. I've also now cleared the background as well. This helps for so every time I move that slider, I can change the position of the arm. So you start to see that maybe what we can do here is put in lots of little steps. But you might also see, and here's the hint, that every time I redraw it, it sort of flickers a bit because it's drawing every last bit again. Okay, so let's go in first though and see how that bit works, how that's different. So I go to my design here. Let's just double click on angle arm and follow through what I've done. So it's very, very simple here. What I've said is the angle, we press that button, it picks out arm angle, which is a global variable, and sends it to the program that says draw Annie. The angle of the arm is picked up from the slider. So it's got a status of the status changed of the slider. I can then go and get the value for it. Let's just go back and look at that because we've not seen the slider yet. There's the slider, and I've given it minimum value of 45 degrees, maximum value of 90 degrees, and I've created an event here that says when you've finished, when you change the state of that, then call this handler. So there's the handler, which then just says, oh, okay, I'll store that arm angle. So then when I press the draw Annie, it sends that. So when I press the draw with the arm angled, it then calls draw Annie with that angle. So let's find draw Annie. There it is, draw Annie. So now this routine takes a double value of theta, and that's the angle from the horizontal that we want the arm to appear at. Everything else in here is exactly the same as what we had on our very simple drawing. Here's the where we calculate the lower arm length. There's quite a big explanation in here, which is handy when you're looking at this later. But then it calculates based on that angle using cos and sine, remember from the trigonometry lesson, from the theta, the angle given, it works out what the x and the y need to be as an offset from the elbow point. There's the elbow point, 250, 130. So it's 250 plus something, 130 minus something to get to that point. There is one slight complication here that cos and sine work in what are called radians. So perhaps more used to using degrees, 360 degrees in a circle. There are 2 pi radians, 2 times the number pi radians in a full circle. So to convert from one to the other, I need to multiply my degrees by 2 pi and then divide them by 360. That gives me radians to go into this calculation. Okay, so depending on what theta we pass, it determines at what angle that arm is going to be at. And the length of that arm we calculated previously from drawing the right arm. Other than that, nothing's different here. We're still drawing straight on to the screen, which is why it's flickering away. Okay, let's go back to the design a minute. The next thing I want to do is to run an animation. So let's look at that. If I press that button, you can see where this is going. It's exactly the same as the construct we used before in creating a timer. We create a timer, we create a timer task, and that timer task calculates within its run what angle we want the arm to be at. So it sends one after another different angles in sequence. So we're trying to create a wave here. It looks for the return value from Annie, which is telling us whether it's false for carry on or true for stop. And exactly the same as in the timer application, if we discover that that is a true, so if stop timer true effectively, then we cancel the timer and we stop and we're ready, and we reset stop animation, which is our global flag, ready for the next run. So everything's determined by this global flag, which is set if we found it. The handler for stop animation will set that to be true. Then finally, within that run routine, we're asking timer to tick every 100 milliseconds, 10 times a second, and to run the task, which is send a command to draw Annie, but at a different arm angle every time. So let's see that run, because you'll find here's the problem. So let's first look at there's angle arm, and we can draw it however we want. There at 90 degrees. Yeah. Okay. If we now run the animation, it's like moving that and pressing that 10 times a second. And you can see the arm is moving up and down here, but the animation is dreadful. I think we already had an indication of that. Every time you hit angle arm, you see a slight flash on the screen because it's rewriting all of those elements every time. And that's what's going on here. So we're seeing this flickering and flashing away. Quite horrible, really. Let's stop that. So I want to work out how to make that into a smooth animation. So let's close that and go and look at how that's done, because this is really the key to all of this. How do we get this to look smooth? We've got the image looking quite good statically. Now we need to make it run smoothly. So exactly the same as the previous one. We set up a timer and a timer task, and we ask it, instead of calling the routine called draw Annie, it's now creating draw Annie smooth and passing an angle. So there's a subtle difference here in draw Annie smooth. There's the routine, draw Annie smooth. So like before, we're passing it theta. The difference, and this is really the nub of this whole thing, is before we drew directly onto the image panel using construct G. Here we have created buffered image. We called it off-screen Annie. So this is an exact copy of the graphics that are on the screen, but these are in memory. They're out of sight. So they're 400 by 400, same size as the image we want to put on screen. Created a buffered image. This type code we've used here says it's RGB and the A says it's got transparency. I'm not going to go into details of that, but that's actually quite important. It allows us to lay down graphics one on top of each other and see what's already there underneath. So we've now got G and we've got O. So O points at the off screen, G points at the on screen. So what we can't see at the background and what we can see. Everything else is pretty much the same, except that rather than writing to G, I'm now going to write to O, the off screen. So I'm going to start exactly the same thing, got anti-aliasing on, etc., different strokes of pens. This is identical. We're just going to write it all though to off screen. Exactly the same business here, calculating the angle of the line. Everything's done off screen. We just scribble it all the way in the background. Then here is the final point, which is really important. Having drawn it all in the memory, we then transfer the whole image off-screen Annie onto the on-screen, which is pointed to by G. So let me just go back for that, because it's so important, because this makes all the difference. G is looking at our real image panel, which we see. So that's whenever we put pixel on that, that's what we see. O is pointing at an off-screen buffer, the buffered image. So this is a picture in memory. So it allows us to do things, all that writing, drawing the head, the nose, the eyes, the dress, filling it in, the legs, the arms, etc., and changing the position of the arms, is all done off screen. Then when we're satisfied that we've got the image we want, the very last thing we do is transfer it on screen. There's a little bit of housework down here. We just dispose of the graphic constructs that we use, otherwise use a lot of memory. So this is the net outcome. Just to show you what happened, we ran that awful simulation. Let's stop that. If we now run the smooth version, there we go. She looks a lot happier. And I can tell you that that smooth animation we're running much faster than the original animation as well. And we can run it a lot faster still if we wished. So that is the key to this whole thing. We've drawn, or we've updated our screen in memory and then only transferred it to the screen, to the visible image, once we've completed all the mucking around with changing angles, etc. In this case only the arm, but it could be much more complicated, as you can imagine, for the scroll. And that's it for this one. The program behind all this is actually written in a very inefficient way to show you the full development. So each button has basically another copy of Draw Annie in it, but they all have their subtle extra bits in them. You can download this example and the timer and the clock, which is the next one coming, and of course the scroll itself from www.redford-tech.co.uk/examples.html. You need to get that all lowercase and correctly spelled out with the HTML, or you won't get there. If you want to contact me, it's simon@redford-tech.co.uk. The little lesson in mathematics and various other notes are also available in this area. And very shortly, the .NET, Visual Basic .NET versions of these programs will also be available, because that's where they started from. So these are all the Java examples at the moment. And over time, I may put some others in there as well. That's it for now. Coming up next is Clock, which just takes us one tiny step further before we finally get to look at the scroll and how that was put together. Thank you very much. See you soon. Bye.